Okay, everyone, now let's talk about something magical, the angle of friction. It sounds fancy because it's not. Because all this is talking about is how do we actually figure out that coefficient of friction? At least how could you do it? Like if you wanted to do this at home. Well, let's talk about it. So you might be tempted to think, okay, well, I'll get a string and I'll attach it to a block and I'll apply a force and I'll just look at a little force gauge until it finally moves. And that could technically work. It might be really difficult, though, to step at that weight and make sure that you're not accidentally moving it before you get a good reading. So what's a way to do it where you can have very, very small changes and get a very, very good answer, at least for what you have access to? Well, we do something a little bit different. Instead of you pulling on that block, you put this block on an angled surface, an inclined surface. And it might not make sense to you yet what's going on here, but it's gonna make sense soon. For example, like just think about it. Look at this block right here. If it had a high coefficient of friction, and I were to, start increasing it, you might guess like, okay, well, the higher the coefficient of friction, it's going to take a longer time before it begins going down the hill. Let's just say super glue on this thing. Well, I can go all the way to 90 degrees. It's not going anywhere. Or something that had very low, you said Teflon on steel. Well, it might be sliding down with just this angle. So a higher angle is a greater coefficient of friction. A lower angle is a lower coefficient of friction. Okay, so we begin to see here what's going on. So if this block is going to remain static, that frictional force has to balance out the weight, which is trying to push it down the hill. If it doesn't, everything fails. Now, remember in this case, we're going to make our axis look like this and this for coordinate system. So weight has a component that's both perpendicular to the surface and it's going to be horizontal, trying to push it down. We want friction to equal this component right there. We want it to equal. Now, angles you can move very, very small increments. Also, that angle, when you calculate it, will have a very, very much smaller value, a much more accurate value, because this is just a little bit easier to do. Changing an angle, you could step it up by the piece of paper each time until it slides. Changing a weight, not quite so easy. So, to measure the coefficient of static friction, remember this is only static friction right here. We just incline the plane until it just slips. You see it slip, okay, you bring it back down a little bit until just before the point where it begins to slip. And then we can determine what the coefficient of static friction is by looking at some angles. So what we see here is we have this angle theta, and there's this angle phi right here, which due to similar triangles is the same angle as that right there. That's going to be pi over 2 minus theta. If you wonder where the pi over 2 comes from, that's just 90 degrees in radians. Okay? Sorry, in radians. For any equation, you always have your angles in radians. Only like the cosine, sine, tangent equations can get away with not using radians. Okay, so we then look at this and we're saying, okay, well, we want to make sure that the weight and the force are blocking each other out. Everything's good there. And so I go ahead and calculate it. And what I'll get from a little bit of calculations here is that my static friction coefficient has to be equal to cotangent of phi. Okay? Static friction coefficient has to be equal to cotangent of phi. So I know the angle, I know what everything else is, I can solve. So this can be a very helpful thing. Now you don't have to do this, luckily. You're lucky that people have done it for you, but you could do this, and maybe I'll make you do it one day. Okay, now when you're solving problems with friction, what's the steps you follow? Well, first, draw a free body diagram, and sometimes it's going to be free body diagrams. You need to show all applicable forces, and you have to decide which way motion is impending. Most times in this class, actually all times in this class, it's not moving, it's just about to move. If you apply just a little bit less force, it'll slide down the hill. If you apply just a little bit more force, it might go up the hill. One or the other is happening. And so you have to decide which one it is. Your frictional forces are always opposing this impending motion. So when forces are all concurrent, it means they happen at the same spot. Well, you just apply your equations of force equilibrium and the friction equation. So you get some of the forces in the x, some of the forces in the y, and also your new frictional force equation, which looks something like that. Now, if they're not concurrent, you can also use your equation of moment, equilibrium. That happens less in these kinds of problems, but it still happens. One thing you're going to run into quite a bit is when we get to wedges, you're going to have to talk about when you have multiple objects, like pushing against a wall or something like this. You have crazy situations and you have to say, okay, this is a free body diagram, this is a free body diagram, that's a free body diagram, and they're all a free body diagram together. Now, if motion is not impending, you can't use this equation right here. You just won't understand what the force of friction is to begin with. Okay, so that's it for this time. Thank you for listening, and I'll see you all next time. Just be on the lookout for those example videos. I'll get them uploaded soon, and you can see some problems being done to solve friction. Have a great day. Bye-bye.